Okay. So, any questions, comments, concerns, queries, inquiries, haikus, etc. before we get started today? If anything at all pops in your head at absolutely any time, do feel free to ask. And let's go ahead and get started. We potentially end chapter 11 today, which should make tomorrow a good review day before a good review day before the weekend, so that we address all your homework questions. Okay. So, we have talked about energy transfer in a couple different ways up till this point. You have heard about energy transfer in a couple different ways up till this point. Last semester, we looked at energy swapping from one object to another, often in a collision, often by changing forms. And now that we've been looking at thermal energy, the transfer of thermal energy really just flows like electricity. It goes from hot to cold, makes things warmer wherever it goes, and makes things colder when it leaves. There's three main established methods of thermal energy transfer. Slightly. Thermal energy transfer. And of the three, we're going to spend today and tomorrow talking predominantly about one of them. But to at least address, we're going to at least address all three. The first and most straightforward means of thermal energy transfer is conduction. And thermal conduction is nice and easy because if two things are touching, then thermal energy is probably conducting between them. This is through direct contact. Sometimes something might say through direct thermal contact, but ultimately that means they are still in a position where they are touching and thermal energy transfers between them. For it to be pure regular conduction, they have to be directly touching one another. If there's something between them, it is still conduction, but it's conduction with extra steps. For instance, I guess it's still conduction if we talk about thermal energy coming through my jacket into the air outside, but that extra layer does change things a little bit. We use the same word here as electrical conduction because really they work incredibly similarly. It's just a flow of something from one place to another. You could describe both of them as current. And in a couple weeks, when we start talking about electricity, we'll get into a little bit more into detail on that. And this is the method that the nerve endings in your skin detect temperature through. It's just, is there a lot of thermal energy conducting through this nerve? In that case, it conducts as a strong temperature reading. Next is convection, which is also just conduction with extra steps. And in what context does the word convection most often get used in a normal human existence? There's a specific process or device where it comes up the most often. Very good, convection oven. So, when you put anything in your oven, let's say object B here is going to be our Thanksgiving turkey. Object A is superheated coils at the bottom of the oven. Typically, you don't put the turkey directly on top of the coils. That will usually make fire and burn turkey and sadness. So instead, you put it on a rack above the coils. Well, if it's not touching the coils, how is it getting its heat? The answer is convection, because there is a fluid medium between the two things, and thermal energy can transfer through. So the footnote here is convection requires a fluid medium. And the term fluid refers to how many states of matter?
2.
At least 2. Very good. Plasma may also count, but good luck getting it on it and then experimenting with it without setting fire to anything. I think plasma's a fluid. It's just a very strange, lumpy, hot electrical fluid. But I'm going to hope that was a pencil falling. So this requires a fluid medium. The coils, or whatever your hot object is touching air. Air is the fluid, so thermal energy will transfer into the air. And you probably heard the statement before that hot air rises. We talked about how with thermal expansion, hot things have a lower density than cold things. So the hot air is less dense than the cold air. That means it's literally going to float upwards. This also causes currents in the ocean as well. Hot water rising, cold water sinking. So hot air goes up, hot air touches turkey, hot air becomes cold air. Now that it has sent heat into the turkey, cold air sinks, and then it touches the coils and gets hot again. So that forms these little convection currents here of just constantly cycling air. And you've probably felt these convection currents yourself if you've ever opened the oven and got a blast of hot air to your face. I have not worn regular glasses really at all in my life until recently when my fiance bought some blue light glasses. She got like 5 of them. So she gave me a pair so we could both wear them while we're watching movies. And I would get up from the movie to go check on dinner, and now I can't see anything. The hot air blasts up and steams up the glasses. Never encountered that before, and I keep forgetting I have them on until it happens. So, interesting things that I didn't notice about life before.
Wait, I have a question.
Yes.
So like, that's like air. So if it was like, let's say water, because I know, I can't think of another example, but when we cook tamales, right, we have like a little bit of water on the pot, and then it boils, and then we have like a little,
Beaver basket?
like a basket on top. So is that the water cooking it, or is that also still the air?
Both. Technically, it's steam and air, which are still both fluids. I believe that that process is you're just steaming the food. So hot steam rises, sends heat into your food, and then cold steam, cold air may sink back down, but steam does like to escape usually. But yes, same thing, same principle, and that would be probably air and steam.
So then how do you do like water? Like, do you use that?
For convection?
Yeah.
Yes, that you absolutely can. We call that boiling. If you just have a pot of boiling water on, throw some. The convection currents will form in the pot of boiling water. They're just harder to, good luck seeing air to begin with. But the boiling water just looks extra chaotic because steam bubbles are constantly escaping. But yes, this does happen in water too. It can happen in any fluid. Don't recommend trying with like gasoline. And second general rule, the heat can only ever rise this way because we're counting on that whole warm things are less dense than cold things rule. So if B was hotter than A, and they were not directly touching, there was just a fluid layer between them. If B was warmer than A wouldn't get any warmer from being beneath it. It's like if you pass your hand under fire.
Under?
Right. If someone's holding like a big lit match and you put your hand under it, there's no danger because the air is carrying all of the heat upwards. Excuse me. So, convection requires a fluid medium and it only sends heat literally up. Or in the opposite direction as gravity is pointing. But some things still basically have to be touching for it to work because both objects have to be touching the fluid in question and they have to be situated vertically. Last method, the one that is hardest to see, except that it literally is the reason Earth has light on it. I'm getting ahead of myself. Radiation. So, this image is a thermal scan of a house, specifically like an infrared scan. They're searching for the infrared radiation coming out of the building. And this is a cold winter's day, so the white patches on the roof likely are literally covered in snow, but that it's not specifically white because it's snow, it's specifically white because these are the coldest parts of the roof. So the brighter the color, like the more bright yellow the color, the more thermal energy is radiating out through this house. And most things, when they're warm, radiate to some degree. Humans do it too. We are technically radioactive. And radiation is interesting because you can just blast thermal energy at anything you want from a distance. Really, a couple different types of energy. You can just blast at things from a distance. And this is especially interesting because it works through the vacuum of space. Space is it's not a perfect vacuum. There's a very thin layer of gas and dust through the void of space. It's just too thin to really do anything with. And it's too thin for any convection to occur, at least this far away from the sun, which means that we're not getting warmth from the sun via convection. We're also not touching the sun directly, so we're not getting our warmth through conduction either. So all of our energy comes to Earth from the sun in the form of radiation. The sun is literally radioactive and shooting us lasers. And technically, this is also why lasers can set things on fire. Light is just to make light, you take energy, you use it to agitate a magnetic field and an electric field. That energy just kind of ripples forwards as the EM wave until it hits something. When it hits something, it tends to be absorbed as thermal energy, which is pretty convenient because Earth would not be bright or warm otherwise. Lasers do this, heat lamps do this, anything warm does this ultimately. This is why thermal, like night vision goggles work. You're just looking for the radiation off by a warm thing.
So it does not require medium.
It does not require a medium of any sort. In fact, it actually travels easiest if there's no medium. Light travels, we consider the speed of light to be constant, but it's less impeded if it's in the void of space and not in air.
So like if we didn't have like, our gases or whatever that we have, we would probably be like burning?
Yes. There's a video that was a big meme a little while back, and hopefully still is, because it's a good video. History of the World by Bill Wirtz. And he just goes through literally the history of the entire planet. And there's one section where he was talking about Earth without an atmosphere, wherein the sun is a deadly laser, because it literally is. Our atmosphere, if we had no atmosphere, you know the pictures of space from the moon, all the moon landing shots? Daytime on the moon, you can see the moon around you, but you look up and it's stars. There's light from the sun, but the sky is still stars. It looks like what night looks like on Earth, because there's no, during the day on Earth, the light has to hit our atmosphere first, and the light tends to scatter and bounce around the entire atmosphere first, which lights the whole sky up. The moon and Mercury don't have that.
Which is why we don't see stars in the day?
Correct. The light from the sun is literally ricocheting around the entire atmosphere, overpowering the rest of the radiation from space during the day. But at night, on this side, where you're not getting direct blasts from the sun, the rest of it is able to more clearly make its way through. This has the effect of A, lighting up the whole sky with color, and B, it diffuses the light of the sun from being a single concentrated laser beam over your head at noon.
So what does the blue, like light blue, come from?
That has to do with the fact that the sun gives off light of every single color, but some of more colors than others. Of all the colors of light, our sun gives off the lowest amounts of violet and green. And all those colors travel and hit our atmosphere, and they start, as it's bouncing around the atmosphere, those colors sort of get filtered out and their energy is absorbed in order from violet to red. There's not a lot of violet to begin with, so that energy gets absorbed pretty quickly. Most of that light is blue, so during the day you see mostly blue, as the colors got refracted through the atmosphere like a prism.
So weird.
Yes, it is weird. It gets weirder when you think about sunset, because what color is the sky at sunset?
Orange.
So does that mean that some parts of the sun shoot different colors of light?
No, because it's the same sun shooting the same lasers at you all the time. The difference at sunset is during the middle of the day, you've got that much atmosphere to get through. At sunset, where the sun is, well, where we have rotated so that it looks like the sun is over here, you instead have a slightly geometrically longer amount of atmosphere to get through. Just due to the geometry, the light has to travel through more air to get to your eye. And the more air it travels through, the more it bounces around and scatters, and the more colors get absorbed by the air. So at sunset, the blue gets eaten up. There's not a whole lot of green to begin with, so that gets eaten up pretty quickly, which leaves us with all the reds, oranges, pinks at sunset until there's no sun left and you just see the violet of the void.
So same with sunrise.
Yes. Sunrise is the same process in reverse order.
Then I don't understand night.
Night?
Yeah.
Night, there's just less light pouring in, which means there's less light bouncing around the atmosphere. Which makes the...
But night is kind of blue.
It is kind of blue, because space is just kind of blue. That might be a little bit of interference from the daytime side of the planet. Because on the moon the void is black. But on the night side of Earth, the sky is bluish purple with stars in it. Again, our sun gives off mostly blue light. So some of that blue might bounce around the atmosphere and make it to even the dark side of the planet. Again, convenient, because that also warms the entire planet at once and keeps us from having a Mercury situation where the day half of the planet is on fire and the night half of the planet is frozen solid. And Earth is very specifically tailor-made so that humans can live on it without having to worry about this stuff. And I just find why the sky is whatever color it is very interesting. It does mean that on other planets with different suns and different gases in the atmosphere, you can have different colored skies. There could be a planet where the sky is just yellow all the time, or green. That's probably more of radiation than I was planning about talking about. I really like explaining this part because when I finally understood it, I was just very pleased with myself. And it's something that most people end up asking themselves their whole lives, why is the sky blue? Subsequently, the next question, why is the grass green? You know how I said the sun doesn't give off a lot of green light? Most earth plants are green so that of all the light coming at them, they're only reflecting the itty bitty little bit of green and absorbing the rest of it for food.
I did that.
Okay.
Didn't know the other one.
So in order, that's why the sky is blue. That's why the grass is green. And when I was a kid, this third question was, why does dirt taste so good? I don't have an answer to that.
It's the nitrogen.
Oh, okay. That's what peanuts taste good too, right? Okay. So let's look a little bit at conduction. We're going to do a little bit of math, but if you had lab this week, you've seen that math before. So, a couple other brief things to remember. Heat flows from hot to cold all the time. It's like electricity. It's going from high concentration to low concentration. And the hotter something is, the more likely it is to give up its thermal energy. Meanwhile, the closer two things are in temperature, the less likely they are to, the slower the process is if two things are at nearly the same temperature. Because when you are specifically talking about thermal conduction, when you're touching anything, the conduction happens because the particles of object A are moving around, bouncing around. They're going to physically collide with the particles of object B. In those collisions, energy gets transferred, like the inelastic collisions from 1500. If there's a big temperature difference, then a lot of energy is going to go in specifically one direction from hot to cold in those collisions between the two objects. But if the two objects are at the same temperature, technically speaking, those collisions are still happening because the particles of both objects are still moving, but they're colliding, they're essentially just canceling out. Any energy sent from one side to the other will get sent back in the next collision. So when two things are at the same temperature, they're considered to be at thermal equilibrium, and the net flow of thermal energy stops. Each individual atomic collision will still trade some, but the average across the entire contact of the two objects cancels out. Excuse me. Now, for the math, we've been using this particular equation to talk about thermal energy flow for a little bit. Power is, this is still the same power formula as 1500, except instead of work, we're looking at energy flow. Power is energy flow over time, still measured in watts. 1 watt is a transfer rate of 1 joule per second. And so you can measure thermal conduction as thermal power, because it's just the rate at which energy is being used or transferred. But there's a couple other things that will affect specifically how thermal energy will transfer from one object to the other. We've already seen the other formula because I believe I made sure to show you this the other day. This is the official finalized formula. When you see this little part right here in the notes, this mathematical symbol looks like an infinity with a bite taken out of it. This is a proportional to symbol. It's not as strong as an equals sign. It just means that if this gets twice as big, then this will also get twice as big, but there's something missing to make it a true equality, mathematically speaking. The thing that's missing from this particular expression is the K term. So scientists did a lot of research. They figured out that some of the factors that affect the rate at which thermal energy transfers out of objects are the surface area contact between the two transferees, the change in temperature from one side to the other, and it's called L, length, but it's really the thickness of material that the thermal energy transfers through. Specifically if you are touching something with your finger, that would probably just be the thickness of your skin. The longer something is, the more time it takes energy to travel through it.
What is the 3 equal?
Come again?
There's like, I don't know, the equal sign for the first equation.
Oh,
yeah.
Thank you. So this is weaker than a normal equal sign because it's not equal, it's just proportional to. This is stronger than a normal equal sign, which is why it's 3 lines instead of 2. This one means is defined as. It's not just that these two things happen to equal the same number. One of them is defined as the other one. So this is, you can look at this as literally what you would get in a textbook definition of power. Power is defined as the flow or use of energy over time.
But it happens to equal that with the constant?
Right. So this is the definition of power. It coincidentally is mathematically equal to this. But in terms of your work in any given homework question, well, you'll never have to use a formula with this in it because you can't. It's not really a formula. If any formula has this in it, why am I stuttering? It's just an equal sign functionally. So you can use it as an equals and proceed with the formula as normal. So, last time, did I mention the case of waking up in the morning and everything in your room feels like it's a different temperature? Okay, good. And I believe we looked at all the variables in this formula, but and we're focusing on just this formula here for right now. This is sort of just the history of how we got to here. It took scientists a long time to finally finalize the constants and get them all measured. So the final thermal conduction formula, you have power, which is the thermal conduction itself, is equal to K, which is a constant depending on what the thermal energy is transferring through. You don't have to memorize any of them because I certainly haven't. Times the exposed surface area the thermal energy can transfer through. This is the difference between, say, touching something with just your finger versus touching it with your entire hand. Or area in question, the faster the thermal energy can move because there's just literally more space to go through. It's like increasing the size of a pipe that water's going to flow through. You also have the temperature differential from one side to the other. Basically, if the difference is bigger, the thermal energy will transfer faster, which is why hotter things feel hotter, because we don't detect temperature, we just detect thermal power, basically. The hotter something is, the more the power it is, because the more energy is going to pour into your poor little hand at once, and probably start boiling the water inside of it, and that's why you get a gouge. Same thing in reverse. The colder something is, the more thermal energy leaves you, the more painful that registers. And then the longer the further the object, the further the thermal energy has to travel, the longer it takes, which is why the L's on the bottom is in the denominator. I still need to get more water.
That's like the function of jackets though, right?
Mm-hmm. Let's see. Now, I'd say most clothing is carbon-based, so there's nothing up here for cotton really, or just raw carbon, but we've got.
But you want a low thermal conductivity, right?
If you want to stay thermally insulated and stay at the same temperature, yes, you want low thermal conduction.
So like we should be wearing nitrogen clothes.
I mean, we functionally are, given what our atmosphere is made of. So we are perpetually surrounded in a nitrogen layer. I actually put it back. Sorry, I'll be right back. But do go ahead and start drawing. I want to point out a conclusion to think about. Notice that the metals at room temperature are freakishly the highest things on this chart. High thermal conductivity tends to go hand in hand with high electrical conductivity. So, brief mental exercise, take a look at these and just track. Yes, that conducts electricity, or no, that doesn't conduct electricity.
Wait, it goes with high what? High thermal conductivity goes with high.
Exception to what I just said a second ago that you may have noticed is water. It's down here at the very bottom. The metals are all up there at the top. Technically speaking, water, I talked about water not conducting electricity.
Yeah.
Okay, yeah. It's the stuff dissolved in the water that conducts electricity. Pure water itself is actually an insulator. So, high numbers are thermal conductors. Energy goes through them very fast like. Low numbers, insulators. So things like styrofoam, not listed here. But, well, this is one reason why we make our houses out of wood. It insulates us from the outside, which is generally pretty convenient. Keeps the temperature inside the building the same. My grandfather always, still to this day, makes a specific joke about, he was very impressed with the first thermos he ever bought as a young adult, because it would keep the hot things hot and the cold things cold, and his question was always, well, how does it know which is which? It doesn't need to know, it just stops the flow regardless of direction. Additionally, our atmosphere is mostly nitrogen, N2, followed by O2, which are, yeah, no, that's air. So the lowest thermal conductivity thing on this table is the thing we're constantly surrounded by. So any insulator we try to put on ourselves to keep our temperature constant is technically worse at keeping us the same temperature than air is. But any layer to keep us from directly touching the air still helps, because the air is what is cold or warm.
So really, when we feel cold, it's actually a lot colder than what we feel because of the air.
Yes. It'll still feel colder the lower the air's temperature is, but for it to feel super cold, the temperature difference would have to be pretty extreme for the conduction to occur in a reasonable time frame. I'd say the biggest reason why like the cold day feels so cold is a combination of the humidity, because if there's a lot of water in the air, that has a higher conduction rate, and the fact that humans have a pretty big surface area, so any wind rushing over you touches basically your entire body at the same time. Also, the wind accelerates this whole thing because the air around you, you are affecting the temperature of, so it's kind of an insulative barrier from the rest of the atmosphere. Because once you change the air around you, the thermal energy doesn't flow as fast. But if it's a windy day, the wind is constantly blowing away the air you've just warmed up or cooled down and replacing it with new, worse air.
And we warmed it up through radiation, or no?
Radiation and conduction.
Okay, yeah.
It's touching us, and also we are giving off radiation. Technically, yes. So a lot of interesting conclusions that one can draw from staring at this table for too long, which is what I've been doing this week, giving this lecture repeatedly. That is okay though, that's what I'm paid to do. So let's just use this principle at least once before the hypothetical bell rings. Put the formula back up over here since it's not on the slide. E equals Ka TH minus Tc over L. We are told about a copper bottom pot. So we know that the material in question is copper. In a second, we'll tab back and copy down the thermal conductivity constant for copper. Sorry?
397.
397?
Yes, sir.
Thank you very much. Excuse me. And you fill it with ice cold water and then put it on the stove. So the stove eye, the hot part of the stove, is going to be our hot reservoir. That's currently at 300 Celsius. What is the temperature of our cold reservoir? Yep, cold as ice. It's not ice, but it's the same temperature. So this is going to inform our temperature differential, and we are then told the physical parameters of the pot. Diameter is listed as 12 centimeters, and its thickness, which is really L, thickness is the length in question, is 2 millimeters. And my M is always in the ends. So, what do we have to do before we proceed with finding power? Yes?
Don't we need to change the units?
Yes, we do. So, how many meters is 2 millimeters?
1.002.
Yep. And diameter?
Divided by square. Wait, how do I know if it's circle?
Oh,
It's a plot. Wait, yeah, but I know.
if it was a question in a textbook, it would probably say so. It might not say so because I wrote it and I assumed a few things. Yes, we're going to assume this pot is a circle. You mean you could make a square pot, but I guess that's just a tub. So this is a round pot with a diameter of 12 centimeters. So what we need is area. We're going to have to turn this diameter into area in meters squared. So the formula for area tends to accept radius better than it does diameter. So in one fell swoop, what would the radius be in meters?
Would it not just be .06?
Okay, yes, the radius is 0.06.
Oh, I'm
Very
sorry.
good. Oh, it's okay.
Yeah.
You did it good. You just got ahead of me, which in general is not a bad thing. The area was, repeat that number, sorry.
0.0113.
Thank you. And that's in meters squared because we converted the meters first before we plug that in. If you use 6 centimeters, your area would be in centimeters squared, meaning you need to convert from centimeters to meters twice. So if you know what unit you need, convert before you put it into area or volume because that just entangles things.
Would you go over 4 places if you did that?
Mhm.
I did not know that.
Well, I like to do my conversions kind of like, I call it railroad style. So let's just, sorry, hypothetical number, 5 centimeters squared. You convert from centimeters to meters, so 100 centimeters is 1 meter.
And then you still have 1 centimeter left, so then you do it again, right?
Yep. If you only did it once, your units would be centimeter meters.
Yeah.
So you have to do it twice, cancel both centimeters and have meters squared instead. So I am in favor of converting before applying to any other formula. But after all that converting, everything is now in a form that our formula can take. So power equals K for copper, 397, times our area, 0.113, times our temperature differential, 300 minus 0. This is basically just a weird delta T, so Celsius is valid as long as they're both Celsius. And on the bottom we have L of 0.002. And then it's just a little bit of calculator foo.
But it's okay if we just change both of the temperatures to Kelvin.
Yes. You are always safest with Kelvin, but this is one of those times where you didn't necessarily need to. But it is always your safest bet in this class. Except for, well, tomorrow we'll look at the one-time Fahrenheit and come up on an assignment other than a conversion.
Do you want this in watts? Or do you just want to put 1%?
Both is correct. Both is the same.
It's just like what they asked.
Right. 1 watt is 1 joule per second, so 6 to 1 half dozen each other.
I got something really bad.
That's completely expected. The reason that's expected is because, looking back at this table that I spent too much time looking at, copper has a really good thermal conduction constant, like better than most of these metals. The only thing that beats it up here is silver, which you wouldn't want to make a pot out of because it will melt. Which is why a lot of people are advertising cooking products made of copper or copper byproducts like brass or bronze.
Is copper magnetic?
Probably. Well, pennies aren't. That's a thing I didn't know. Actually, okay. When in doubt, I just literally looked it up. No, copper's not magnetic.
Because I have a stove that only likes magnetic, like, hot. And, like, I don't,
Oh, an induction stove.
yeah, and I don't know, like, why.
It's, you guys are free to go. I'm not going to hold you. Have a wonderful day, but I am going to answer this question if you're curious. I am still trying to figure out induction stoves because when I bought a new house, I had to figure out if it was an induction stove and figure out what pots and pans were going on. It's not an induction stove. Avoid that complication. But whereas normal stoves make heat and then send it into the food, an induction stove doesn't make heat. It instead just sends electricity through a magnetic coil and is emitting a magnetic field that then warms up magnetic objects.
But it is hot. Oh, but it's hot because of probably conduction. It's the pan is touching like the rest of the stove, like that kind of thing.
It's less to do with thermal conduction and more to do with magnets. They use magnet magic to make it hot.
Yeah, because like if you turn it on, it doesn't get hot until you put the pot.
Right.
Yeah.
This is-
Okay, that makes sense.
Whereas fire just makes thermal energy, and whereas most electrical stoves will use the electricity to make thermal energy, the induction stove just activates a magnetic coil, and the magnetism is what affects the specific pan and makes that warm, kind of like how the microwave only warms up water or metal. That can also be a form of induction. Because if you just put if you just put an empty coffee mug in the microwave and turn it on, nothing happens.
I didn't even know that. Oh my god.
That's okay.
That makes sense.